Hello everyone and welcome to day 3 of notes on probability and statistics. This one will be over mutually exclusive and inclusive events. To get things started, we're going to have a practice problem. Now in event A, we want to get heads when flipping a two-sided coin. In event B, we want to roll 5 on a standard 6-sided die. So we have these two events. And whenever you have two events, there are technically two types of problems that could occur. The first problem is the probability of A and B occurring. You could almost say occurring at the same time. All right, versus the probability of A or B. You could finish that one up with happening at all. Okay, so if you want the notation for these, this is going to be probability of P, A, and B. Okay, it's kind of that upside down U. And the notation for an OR equation would be A and B, like that. And to kind of illustrate what's happening here, if we had a Venn diagram of sorts, and this is A over here, and this is B over here. When we're dealing with A and B occurring, we don't care about if A happens by itself. We don't care about if B happens by itself. We want to know when A and B happen at the same time, when they occur together. And so we're actually looking for only this overlap right here, of when A and B both happen. Whereas for our OR probability, if we were to have A and then B, okay, all we care about is if A happens. So if A happens, we're good. If B happens, we're good. If they both happen, awesome. We don't care about them being together. We just care about if they happen at all. And so this Venn diagram is going to look like 100% full. Because like I said, if A happens, we're satisfied. If B happens, we're satisfied. If it both happens, we're still good. Okay? So that's an illustrated picture of the difference between A and OR and probabilities. So, getting back to our problem, to show you how this would work in a real problem, let's just go ahead and do a quick sketch of our sample space. So if we have a heads when flipping a two-sided coin, that's event A. So the two possible things that could happen is I could get a heads or I could get a tails. Okay, those are my two possible outcomes for event A, heads or tails. Now for event B, I want to roll a 5 on a standard 6-sided die. Here's where things get fun, because I can roll a heads and a 1. I can flip heads and roll a 2. I can flip heads and roll a 3. Okay, these are all the possible outcomes that could happen. And I could do the same thing over here with my tails. Tails and 1, tails and 2, tails and 3. Okay. Now, for my AND equation, so if I want to know the probability of A and B happening together at the same time, then that's going to be the probability of heads and the probability of a 5, which means probability of getting a heads is 1/2 times the probability of getting a 5, that's 1/6. My answer is going to be 1/12. And sure enough, if you count your sample space, you have 12 options total, but there's only one where you have both a heads and a 5. Okay? Whereas if we were doing the OR equation, so probability of A or B happening, okay, probability of a heads happening or a 5 happening, okay, all of these are heads, and then not only do I have a 5 here, but I also have a 5 here. So the way this is going to look like is I have probability of a head, so 1/2, plus the probability of getting a 5, which is 1/6. Okay, so when I want the AND, I'm multiplying. When I want an OR equation, I'm adding. But notice how in our Venn diagram, this overlap section is kind of counted twice. It's counted when you include the odds of A, and it's counted when you include the odds of B. So you will need to subtract that overlap. And as we found out in the AND equation, the overlap is 1 over 12. Okay? When you simplify that together, it is 7 out of 12. And sure enough, if we were to count out of our 12 options, the number of favorable outcomes that could happen are 7 out of the 12. Okay? So this is the AND versus OR probability, which leads us into the rest of our lesson. Mutually exclusive events and inclusive events. So if two things are mutually exclusive, it means they don't have anything in common. They don't have any outcomes in common at all. All right? If two things are inclusive, it means they're not exclusive. Okay, so mutually inclusive means they don't have anything in common, and if that is not the case, then they are inclusive events. Okay, and there's an example in the next slide where it might make more sense. But we have two equations when we talk about mutually exclusive and inclusive events. For exclusive events, we're adding the two probabilities together. Probability of A plus the probability of B. For inclusive events, we are adding the two events together, but then we have to subtract the overlap. Okay, because if they're inclusive, it means that they do overlap. Okay, a bit of an illustration on this one. If a mutually exclusive event, that means I have option A, probability of A, and probability of B. There is no overlap between them. Therefore, I just have to add them together to get my answer. For inclusive events, they do have something in common. So go back to that Venn diagram. Event A and event B do overlap. So while you can add the two events together, you also have to subtract out your overlap. Otherwise, you're counting something twice. So here's some examples. And we want to determine whether the events are mutually exclusive or inclusive, and then why. Okay? So the first problem, selecting a number at random from integers 1 to 100 and getting a number divisible by 5 or a number divisible by 10. So 5 divisible by 5 and divisible by 10. So our first thought is can you have a number be divisible by both 5 and 10? And the answer to that is yes. So there is an option where these two events overlap, which means this will be an inclusive event because numbers can be divisible by both 5 and 10. All right. Next one. When you're drawing a card from a standard deck and getting a 5 or a heart. The question is, can you draw one card and it be both a 5 and a heart? The answer to that is yes, it's the 5 of hearts. So again, this would be an inclusive, all right, because the 5 of hearts exists. Last one. Getting a sum of 6 or a sum of 7 when two dice are rolled. Okay, and I'm going to add standard dice, standard 6-sided. Okay, as a clarification. So getting a sum of 6 or a sum of 7 when rolling two standard 6-sided dice, this would be mutually exclusive. Okay, because you can't roll the dice and there be a number that adds up to both 6 and 7. It either adds up to 6 or it adds up to 7. Those two options don't overlap. So this would be mutually exclusive. Because the sum is either 7 or 6. So that's kind of how you start off the problem. And once you figure out whether it's mutually exclusive or inclusive, then you can use your two equations and solve for the actual probability. So let's go to this slide. First problem, two dice are rolled. What is the probability that the doubles are rolled or that the sum is 9. Okay, so doubles are rolled or the sum is 9. Now, if you want to illustrate your sample space, this might help, but the doubles will be the 1 and 1. It'll be 2, 2, 3, 3. Okay, 4, 4. It's a bad 4, but I stand by it. 5, 5, and 6 and 6. Okay, if you add up any of those, you notice that none of them add up to 9. So this will be a mutually exclusive event because there is no overlap between them. Okay, so I'm going to do the probability of doubles or sum is 9 because it's either one or the other. Which means my mutually exclusive equation is just adding those probabilities together. So the probability that doubles are rolled would be 6 out of 36. Because there's 36 options, but there are only 6 doubles, plus 4 out of 36. And again, if you want to draw your sample space, that may help you see what's going on here. Or you can just take my word for it. But your probability is 5 over 18. Okay. Next problem. What is the probability of drawing a king or a diamond from a standard deck of 52 cards? So the question is, can you draw a card and it be both a king and a diamond? Answer to that is yes, the king of diamonds. So this is an inclusive problem. And so when we do the probability of getting a king or a diamond, there's going to be an overlap, the king of diamonds. So we got to make sure we subtract that overlap, that way it doesn't get counted twice. So the probability of getting a king is 4 out of 52, because there's only 4 kings. The probability of getting a diamond would be 13 out of 52. And then we got to subtract the 1 king of diamonds. And your answer, when you add this all up, you'll have 16 out of 52. Simplify that further, and you get 4 over 13. Now, I will say right now, we got lucky on these two problems because we had a common denominator. But don't forget that in order to add or subtract fractions, you need that common denominator. So if you don't have one, then you'll have to multiply your fractions in order to get one. All right, now so far we've only been talking about the probability of something happening. Okay, what is the probability of getting a king and a diamond, or a king or a diamond from a deck? Okay, 4 over 13 is the probability of that happening. An equally valid question, though, is the probability of something not happening. Okay, this is called the probability of the complement. Now, as a brief point of explanation, whenever you have a percentage, let's say I have 90%. When I write that as a decimal, I have 0.9. Okay, so 0.9 is 90%. Therefore, 100% is going to be 1. Okay, so the closer a decimal gets to 1, in percentage terms, that means it's getting closer to being 100%. It's going to happen. Now, the probability of something not happening is going to be 1 minus the probability that the event will happen. Okay, so you see the equation down there. So probability of P, not A, is equal to 1 minus the event occurring in the first place. So as an example, if the chance of rain is 70%, what is the chance that it will not rain? Okay, so if we have 1, or we can even do percentages. So if there's a 100% chance of it raining, minus the shot of it raining, then you're going to get a 30% chance that it won't rain. Okay. You could also write this as decimals and plug it into the equation if you want. So if I have 1 minus 0.7, then I'm going to get 0.3 as my solution, and then it's 30% either way. Remember, stats isn't so much about equations, it's about applying logic. So when in doubt, try to find the logic in the problem first. Let's do another example. All right, so in this one, Francesca bought 20 raffle tickets hoping to win a $100 gift card. If a total of 300 raffle tickets were sold, what is the probability that she won't win? AKA, what are my odds of winning? So Francesca brought 20 raffle tickets hoping to win the $100 gift card. Now, the $100 is just there to throw you off. It's just extra information about the problem. We care about the total number of raffle tickets and how many she bought. So the probability of her not winning, so probability that she won't win, is going to be 1 minus the probability that one of her cards gets drawn. So she bought 20 out of the 300. This is the probability that she does win. Okay, when you simplify that, it'll be 1 minus 1 over 15, which means the odds of her not winning is 14 over 15. And that is your final answer. Okay, now in the notes, I think there's one more problem. I took that problem out because it's a bit more complicated than we're going over right now. It's still a good problem. If you have questions on how it works, please let me know. However, in this video and on the quiz, I won't be using that problem. So this last slide that I'm going to show you, this is a good summary of everything that we went over. So it includes independent events, dependents, conditionals, mutually exclusive. You can read the rest of the chart. I will add that please make sure you know the probability of A and B, plus its notation. Sorry, there was a tab that came down. I want to go away. So probability of A and B, as well as the probability of A or B happening and its notation. Okay, so you want to know the notation, you want to know the Venn diagram, and kind of be able to explain and solve. So that whole first slide is still important. All right, and that is the end of this video. That is the end of the PowerPoint. Again, that last problem, I think it's about drivers not wearing their seatbelts. It's a good problem. If you want to talk to me about it, we can go over it, but it will not be on the quiz. Other than that, have a good one. Please let me know if you have any questions.